Yes, good morning. My name is Bosco Tran. I'm the Structural Manager at ASC. So my involvement with the Collins class dates back on and off since 1988, so it's a long time. So I started my life as a defence aerospace, and then went joined companies in Sweden for about 3 years before I came back to Adelaide. So I hope to give you a bit of an insight of what we do. Unfortunately, due to defence security rules, I can't share too much information, and there's copies. So we'll just talk a little bit about ASC, what our role in the Collins class, and what it involves, what the structure department does, and what we actually use to get there. So there's a couple of pictures there. The one on the top right, and your right, it's actually the site around 1987 when the company started. It started with actually 4 parties. Those of you who are actually ASC may not know. It's actually ASC is a Australian submarine consortium formed between the AIDC, which is the Australian Industry Development Commission. Second part is Wormald. There's Cockham's and also Chicago Region Iron. ASC got the contract to build the submarines, they subcontracted the design to Cockham's, but actually the combat system was led to within Rockwell ship systems, so under a separate contract with Commonwealth. We delivered 6 boats, Collins in 1996 and right all the way up to 2003 for Rankin. Can I just ask one quick question? Do you know when the Collins program actually started, from concept to something? Any idea? 1982. So a contract was awarded detailed design phase 87. It was launched in 94, so it actually took about 4 years. Picture at the bottom there, it's actually not the latest picture. There was a time when, before the air warfare destroyer was awarded to ASC. Now it's actually a bit more developed than that. So 2005, and we also built we're doing the OPV, which is offshore control vessels. So our primary role is to maintain the Collins class. But it's actually more than just maintenance and restricted parts. Take a component out at full cycle docking and maintain it. We do a lot of design enhancements. As you can probably imagine, a lot of components wear out and they become obsolete. So just give you a bit of a snapshot there. We've done combat systems upgrade. We've heavyweight torpedoes. It's just simply, not just simply put heavyweight torpedoes in, it's actually the whole arrangement from the outboard and embarkation ramp, down the ramp all the way down to all the weapons handling equipment on board, all the rigging. So there's modifications involved in those. We've done special forces, multi-swing release, and there's whole heaps of other things like sewage automation. We've done shuttle hull valves. Head-on firefighting systems, even right to this day, we're still doing special forces modifications as time goes on. See at the bottom there, there's 2 things. There's obsolescence and life type extensions. Obsolescence become one of the key focuses now because both 1987. So in fact, you remember IBM 486 was actually, that's how a computer system was back then. So you can see there's a lot of changes. Probably feel that way. Not saying life type extension. So I've got some slides to look at that. That's what we're talking about now. It's lengthening the life of the boat. Originally, it was scheduled to be finished in the 2020s. 25 years. Now, but we're talking about now 20-year-ish expansion. It's a very busy slide. Why did I show you this? Because submarine's got over 100 systems, and to perform that well, we actually do require a lot of skills, and the structural department, the elements of it, form one snapshot of it. and the FEA is actually another smaller component of that. So that's all I want to say about that. So structure department, we form 4 functions: naval architecture, structure design, noise and vibration control, and material testing. So there's some interesting pictures up there. On the top to the right, actually the Collins class, in this case is Rankin, undergoing the Submarine shock trials. That was back in 2003. Some of the members here actually went on board while the web charge was set off, so it was quite exciting. And down the pictures down in the middle is the explosion bulge test. The one on the right hand side is the material testing lab, which is now accredited. So basically, naval architecture, we do support the docking. I won't read, because you can read all that. But in the structural design, in particular, we do submarine structural analysis, and you might say, well, what is there to analyse? Isn't the boat already built? Well, the answer is there's always design upgrades and enhancement. The boats wear out. You don't always replace with new. There's a lot of corrosions, there's rust, there's stress concentration. So we do a lot of modern aspects. Shock and vibration, of course, pressure vessels and piping. Heavy lift and handling. So the bottom picture there, this particular one here, that was required because in order to get the full site production from 4 years down to 2 years, there were workflow analysis that showed that the components actually maintain outside float to actually lift it out, actually would enhance the throughput. So a lot of finite modelling was done on the pressure hull. The pressure hull actually sat, submarine sat on the hull cradles, and what was of major concern is that if you actually cut a hole in the top of the submarine, what happens to the steel? It actually changes shape, and the change of shape has major contributions for the outer-rounders and the straightness, and it can be detrimental to submarine safety and stresses. So there were reinforcements. There was some reinforcement there, you can see. So the idea there is to maintain the shape while we actually cut it along with signatures and controls like that. So what do we use ANSYS for? We've been using it since 2007, I think. I have to check my records, it's been a long time. We migrated from Submarine, so we don't do a lot of CAD geometry. It's been imported through our design department. Stress analysis, probably in the most part, what we do is static stress analysis. I would hesitate to say, whether it be 50 or 60%. I won't put a figure on that. But the majority of this is these days it's more on in-service parameters, corrosion and stress concentrations. We talk about piping, we talk about valves, we talk about mass integration, fin, and of course a submarine hull. So if you look a bit further, there's fatigue assessments. Got some slide about fatigue in the moment. Shock analysis is a very big thing for us. Many components are isolated. We cannot isolate everything on the boat. The hull valves are now constructed boats, so they see a lot higher shock input. Our primary response is actually the shock spectrum response. We don't tend to do as much transient analysis time. For main reasons is that it's very, very time consuming, and we also have a very strict standard response spectrum that we have to comply with. Thermal analysis, and there's some non-linear elastic structural analysis that we do on the pressure hull at the moment for the lifetime extensions. The second last point, the stress concentration factors. That was a study done on the pressure hull, because you can imagine maybe corrosion pit comes in different shapes and sizes. The square, the oval, it can be all different shapes and sizes. So a study was done to determine what stress integration factors you would see. The reason is, well, why do we need to know? Because we don't actually reinstate the material in all cases. If we can actually leave it as it is, then great, or we can blend it, or we can actually reinstate by re-welding analysis. Okay, so the life type extension project, why do we need to do it? Is because the current planned draw date is in the 2020s, and Naval Group new submarine program is actually a bit slower than we would have liked for all kinds of reasons. So there is a gap as far as the submarine community is concerned. Hence, the involvement in the life type extension. It's not just the structural component, it's a whole bunch of mechanical, electrical, combat systems works. So, my apologies, I can't show you any details, but if I can explain briefly the process that's involved, a snapshot of it. Start off I'm giving you an example here on fatigue modelling of the pressure hull, and start off with the life cycle. Fatigue analysis done by fatigue tool in ANSYS with the SN curves, and there's a modified SN curve that we apply. We undertake fractional mechanics assessments on localized joints. We're applying specific localized joints where our stress analysis tool by fatigue tools actually show the points of failures, and what we talk about the benefits still later. So on the top right here, these are not real life cycles that were made up. So on the top right, the top left here, you see the blue and red. So the blue was hypothetical, in this particular case, life cycles, and the red is actually our projected based on the worst load in usage, and we project that forward. That's get fed into the ANSYS, and on the top right is the brain flow count. Down at the bottom here is a whole bunch of estimate curve. In the British standards, there's different weld classification depending on the joint. In the modelling of the boat, we use shell elements, and as a start, we use F2. We might say, well, why F2? F2 is actually partial penetration joints that people fillet welds and that sort of thing. But our boat is actually full penetration welds between the frames and the hull plate. But we do have bracketry on board the boat, so it was conservative for us to use F2. You have to downgrade this. These curves are in the air. You have to downgrade them because of seawater effects, and you've got to take into account this variation in material, so a standard deviation has to be applied to that. Yeah, so that's what the okay, these are a fictitious submarine hull. Just to give you a process, the modelling was done basically with shell elements, and details using the fatigue tool came out that actually showed a usage factor over our 50 limit. Some modelling was actually conducted, and this is a hypothetical facility. In the British standard, when you actually undertake localised modelling, it allows you to use a pass, joint pass dead, and a spot hotspot method can actually be used to linearise the stress, so you don't actually have the stress right at a sharp corner, for instance. Joints that actually showed failure, we undertake the fracture mechanics. We don't use ANSYS for that. People have actually written a code in our department for further evaluation. So Why are we doing all this? The reason being is, the primary reason is the outcome is a test plan and inspection test plan, so that it minimises the area that we have to go and do detailed EPT. That's really kind of focus. And should there be a critical joint that we can't overcome, then naturally there'll be potential redesign of the joints. So that's it for me. I'm sorry I'm reading into your.
Any questions for Bosco? Yeah? Well, thank you very much.